Imagine you are at the controls of a Boeing 787 Dreamliner. You are hurtling through the air at 560 miles per hour. Beneath you is a machine that weighs more than 200 tons, roughly the weight of a massive blue whale. Every time you move your wrist just a fraction of an inch, this giant responds. The nose lifts, the wings tilt, and the entire structure shifts with surgical precision. How is that possible? How can two human beings, sitting in a cockpit no larger than a walk-in closet, dictate every movement of such a massive object? The answer lies in a century-old dance with the wind, managed by 3 simple axes and a high-tech nervous system. Driving a car is relatively simple. You turn the wheel to go left or right, and you press pedals to speed up or slow down. You operate on a flat, two-dimensional plane. But in the sky, there is no flat. A pilot has to navigate a 3D environment where the aircraft can move in 3 distinct ways at the same time. This is what we call the 3 axes of flight. To master the sky, a pilot must control the airflow around the plane. If you control where the air goes, you control where the plane goes. Surprisingly, whether you're flying a small Cessna or a massive Airbus, a 380, the basic steering wheels are almost identical. To understand aircraft control, you have to visualize 3 imaginary lines passing through the center of the plane. The longitudinal axis, running from the nose to the tail, roll. The lateral axis, running from wingtip to wingtip, pitch. The vertical axis, running straight up and down through the center, yaw. Every maneuver a pilot performs, from a gentle turn over the Grand Canyon to a steep descent into LAX, is just a combination of these 3 movements. And every movement is executed by manipulating specific control surfaces on the outside of the plane. If you want to turn the airplane, you don't just turn the wheel like a car. You have to roll. This is controlled by the ailerons, the small hinged panels located on the trailing edge of each wing. When a pilot moves the side sticker yoke to the left, the aileron on the left wing goes up, and the aileron on the right wing goes down. The wing with the upward aileron loses lift, while the wing with the downward aileron gains lift. This imbalance causes the entire 200-ton machine to tilt, or bank, into the turn. It's a masterclass in Bernoulli's principle. We are intentionally making one wing worse at flying for a few seconds to force the plane to rotate. Think of it like riding a bicycle. When you want to turn left, you don't just jerk the handlebars. You lean your body. That lean is what actually initiates the change in direction. An airplane's roll is exactly the same. By banking the wings, the pilot redirects a portion of the wing's lift to the side, pulling the airplane into a smooth, curved path. Without this ability to roll, an airplane would be as clunky and unmaneuverable as a train on tracks. To make the airplane climb or descend, the pilot controls the pitch. This happens at the very back of the plane, on the horizontal part of the tail, called the horizontal stabilizer. The movable parts here are called the elevators. When a pilot pulls back on the controls, the elevators move upward. This pushes the tail of the airplane down. Because the plane is balanced like a seesaw, when the tail goes down, the nose goes up. Suddenly, the wings are hitting the air at a steeper angle, creating more lift and sending the plane climbing toward the clouds. Conversely, pushing the nose down allows the plane to slide down an invisible ramp of air toward the runway. The final movement is yaw, which is the nose moving left or right without tilting the wings. This is controlled by the rudder, the large vertical flap on the tail. In modern flight, the rudder isn't usually used to steer the plane in the air. That's what the ailerons are for. Instead, the rudder is used for stability. It's critical during takeoff and landing, especially when there's a crosswind blowing the plane off center. If the wind is pushing the plane to the left of the runway, the pilot uses the rudder to kick the nose back into alignment. It's the finishing touch that ensures the plane stays pointed exactly where it needs to go. For the first 50 years of aviation, pilots were connected to these surfaces by thick steel cables and pulleys. If the wind was strong, the pilot had to use physical muscle to move the controls. But as airplanes got bigger and faster, the forces became too much for any human to handle. Enter fly-by-wire. On a modern jet, the pilot's steering wheel isn't connected to the wings at all. Instead, it's connected to a computer. When the pilot moves the stick, they are sending a digital request. I would like to bank 20 degrees left. The computer then calculates exactly how much to move the ailerons, adjusts for wind speed and air density, and moves the surfaces using powerful hydraulics. To understand the true genius of modern aircraft control, we have to look closer at fly-by-wire FBW. In older legacy aircraft, if a pilot panicked and pulled the controls back too hard, the plane would tilt its nose up until the wings lost lift and stalled, potentially falling out of the sky. But in a fly-by-wire system pioneered largely by Airbus and now standard on almost all new Boeing and Embraer jets, the flight computer acts as a high-speed filter between the pilot's hand and the aircraft's wings. This system operates on a logic called control laws. Imagine you are driving a car that is physically incapable of letting you drift out of your lane or flip over, no matter how hard you turn the steering wheel. That is exactly what FBW does for a 200-ton jet. If a pilot tries to bank the plane more than 67 degrees, the computer simply stops the roll. If they try to fly too slow, the computer automatically increases engine power. It is constantly performing thousands of calculations per second to ensure the plane stays within its flight envelope, the mathematical safe zone, where the physics of lift and drag are perfectly balanced. But the benefits aren't just about preventing mistakes. It's about efficiency and fatigue. In the old days, pilots had to constantly trim the airplane, making tiny adjustments to the controls to account for weight shifting as fuel burned off or as passengers moved around the cabin. In a modern FBW aircraft, the computer handles these micro adjustments instantly. It senses a slight drop in the nose or a tiny gust of wind and corrects it with the elevators or ailerons before the pilot even notices. This creates a smooth feeling that was impossible 40 years ago. It allows a massive aircraft to feel as light and responsive as a small fighter jet. Furthermore, because there are no heavy steel cables running the length of the fuselage, the aircraft is significantly lighter, which saves millions of dollars in fuel costs every year. It is the ultimate marriage of silicon and steel, ensuring that even in the most stressful situations, the laws of physics are being enforced by a computer that never gets tired, never panics, and never misses a detail. Despite all this automation, being a pilot is still one of the most demanding jobs on the planet. The skill has shifted from moving the cables to managing the systems. A pilot at 35,000 feet is a high-level manager. They are simultaneously monitoring the fuel flow in the engines, the weather patterns 200 miles ahead, the traffic in the surrounding airspace, and the health of the electrical systems. They have to stay 5 minutes ahead of the airplane at all times. The complexity isn't in moving the rudder. It's in knowing exactly when and why to move it. While the cockpits have changed from wooden sticks to glass screens and computers, the air itself hasn't changed. The physics that the Wright brothers used in 1903 are the same physics used by an Airbus, a 350 today. It all comes down to managing the invisible fluid around us. If you can control the airflow, you can conquer the world. The next time you see a massive jet silhouetted against the sunset, remember, that giant isn't just drifting. It is being held in a precise, three-dimensional balance by a pilot who understands the secret language of the wind. Aviation is a world where simple physics meets impossible engineering. If you found this breakdown helpful, there's a whole lot more to explore, from how jet fuel works to the secrets of the black box. Make sure to hit that subscribe button and join our community here at Aero Explained. We're dedicated to making the complex world of the skies clear for everyone. Safe flying, and we'll see you in the next one.